Hey,
Hey, Freddie, how's it going?
it's going all right. How are you?
Yep, doing all right. Just had a pre-calc exam for 2 sections.
Cool.
Yep. Hey, Ms. Zolos, how you doing?
Really good. How about you?
Doing all right. Doing all right.
Are you ready, Makoto?
No, I'm still typing up my slides right now. It's like, I regret not giving a talk earlier because I imagine you had all your slides like ready way before me, right? So
Yes, I give the same, virtually the same talk.
yeah, so this is no, I'm still like halfway through.
Is it tomorrow? Is that right?
No, it's next week. If it was tomorrow, I'll be a lot more worried.
okay.
I wouldn't be here. I would not be here if it was tomorrow.
I knew it was a Tuesday, and so I was like,
no.
I was surprised I had forgotten if it was tomorrow. So that makes me feel better. Okay.
Yeah, I mean, because like Laura hasn't even sent emails around, I think so.
Right.
Oh, right. Good.
Yes, I think she sends it 1 week before or the week before and then 1 day before.
Yeah, I think that's great. Yeah. Have you finished submitting the what they call format check, Mendoza? Or are you just gonna do it one go?
Oh no, I actually have finished this because the deadline is 29th of March. You might want to do it too. They don't really care about the month. They just want to see if you have done the format correctly. So they found 2 mistakes on mine.
Yeah.
So just put it in and then you can revise and put the final version once you're done.
Yeah. I'm just curious if you have done it already.
Oh no. I'm waiting for Pete to give me his corrections to put the final. I did the initial one, but I haven't put the final one.
I see.
Yeah, don't forget about it. It's actually very important because I think you have to pay if you don't do it on time.
Oh really? Damn.
Yes, I think it's $50. So don't.
That's hilarious.
Like for the format check, like the first thing.
Yeah.
So are you excited though, Makoto?
No, I just want to be over. Like, I'm looking forward to the day after submit my dissertation and be free. That's what my motivation is right now.
Will you be around the summer or will you?
Yeah, I think I'll be around till July probably.
Have you asked for funding or no?
No.
Funding
is pretty low as is. You don't need any older people trying to get money.
I see.
All right, well, welcome back, everyone. So so today I mean to complete the proof of local class field theory for p-adic fields. The method would give much of local class field theory for Laurent series fields, not all of it. And then for that matter, I actually think the method that I'm introducing is arguably even more important than local class field theory itself. So should be a good day. But any questions before we begin? All right, I guess we'll get into it then. So so here's a result that I wrote down. So some statements to see what's coming. I don't think I came back to the second part of this looks very complicated. We get very close to something that looks like this statement at the end of this lecture, but I still think we're not. It seems to me that we're not using the statement in the second part. So let me maybe not even worry about the second part. So the first part is actually just passage to the limit on something that we've already done. So we have a character on the Galois group of our local field. We have an element of our local field. And so then what are we doing? We're taking a B, which we're thinking of as living in a NH0, and then we're cupping it with, again, there's as we've seen many times, there's the co-boundary map gives an isomorphism from the character group of our field, any field really, H1 Galois cohomology with coefficients, first Galois cohomology with coefficients in Q mod Z, so that's a hom from the absolute Galois group into Q mod Z, which is by definition the character group. And then the co-boundary map gives an isomorphism to second Galois cohomology with coefficients in Z, because the third term is Q, which is as cohomologically trivial as it gets. Okay, so this cup product is taking place, let's see, in, yeah, so the Z tensored with the multiplicative group of the field. So this is living in the Brouwer group. And so by the invariant isomorphism, we stick it down into Q mod Z. And so, yeah, so by doing this relatively complicated looking thing, it ends up just evaluating the reciprocity map, which gives us an element of the abelian Galois group, and then we apply the character. Okay, and so the point is, this is really passage to the limit from something else. So here it tells me to go back to page 2 of this lecture. We proved this. Yeah. So this is what we proved. We've already proved this at any finite level. Okay, this was a key fact. It looks a little bit technical, but it's kind of always helping us basically. So you're just trying to string some equalities together, and if you use this expression, then you get useful information about the reciprocity map. Okay, and so again, yeah, part B. First of all, I copied this directly from Harari, and there really seems to be a characteristic assumption missing for this to be true. It's kind of this map again. It's actually going to come up at the end of the lecture, but yeah, I don't think. I could be wrong. Anyway, if we did cover it, it would be a finite coefficient sort of analog of the previous result, and it would follow just from some routine properties of cup products. So I'm referring you to page 122 of the textbook, is where this result is stated, and it follows from some properties of cup products that are discussed on page 49 of the textbook. But yeah, you see that it's basically it's kind of it's an analog of part A, only instead of landing inside Q mod Z, things are landing in mu n. Okay, or some things are landing in Z mod NZ, and some things are landing in mu n. Okay. Just think about this for 1 second. Yeah. Anyway, so I actually don't think we need this, but all right, so let me go on to, at the moment, so just kind of by review, what do we know at the moment? At the moment, we have our reciprocity map, which we defined at every finite level, which gives an isomorphism from K star modulo norm of L star, where L over K is any finite abelian extension, to the Galois group of L over K. And then we had this result where here was where the proof was, it seemed to me that there might have been a gap in the proof, but we went with it. Where was the result? Here, yeah. So if you have this is just saying that these isomorphisms that I was describing before are compatible with the natural inverse systems on both sides. And so therefore you pass to the limit over these isomorphisms, and you get a reciprocity map from the inverse limit of these guys, which has a map, K star maps into that with dense image. So the inverse limit of K star modulo the norm subgroups is isomorphic to the abelian Galois group of K. And then again, the only question is, yeah, so here we get exactly what I'm saying. We get this map. So this is an isomorphism, okay? But then and then we know it's actually it's clear, I hope, from this description, that this map is dense. That's an isomorphism. So therefore, if I pass to the profinite completion, I definitely get a surjective homomorphism. But the question is, what's the kernel, right? And so I talked about that as well. Let's see. So this is where we stopped actually. So we showed everything else. And so yeah, so by passing to the profinite completion on the reciprocity map, we get a surjective homomorphism from the profinite completion of the unit group, which we know is just the unit group of the field, which we know just by a choice of a uniformizer is isomorphic to the unit group of the ring cross z hat. Okay, so the profinite completion is doing something very innocent over here. And then the question though, so therefore, if you have a surjective homomorphism of profinite groups, then you're just going to have an isomorphism modulo the kernel. Okay. Because a continuous bijection of compact Hausdorff spaces is a homomorphism. Okay. And so the only remaining question, in fact, is what is the kernel of this map? And then formally, the kernel of this map is the intersection of all the norm subgroups. Okay. And so the remaining question is sort of to show that there are enough finite abelian extensions such that the intersection of all the subgroups that you get by taking norms from the finite abelian extensions is trivial. Okay, so that's called the existence theorem, that there are sort of enough finite abelian extensions in order to make this intersection trivial, or equivalently, in order to make the original reciprocity map omega. Is that? Yeah. So now, if you know that kernel is trivial, then omega is an injection with dense image, and therefore induces an isomorphism after you take profinite completion. Okay. So the last thing that we're trying to do is we're trying to show that we have enough abelian extensions to have the norm subgroups do what we want. I guess an equivalent statement here is that equivalently, we would like every finite index, we'd like every open subgroup of K star to be the norm from a finite abelian extension. Okay. Any questions before we go on and introduce the tool that will prove that for p-adic fields? No questions? All right, well, here we go. It's exciting. So the tool is local symbols, okay? The particular type of symbol I'm going to introduce is, depending upon taste, is either called the norm residue symbol or the Hilbert symbol. Okay. Sometimes the Hilbert symbol is used only for the n equals 2 case, and sometimes it's used for the general case. Okay. And the point is that this really is much more general than just local class field theory. Okay. In fact, I can define these norm residue symbols whenever I have a field. So there's the norm residue symbol is mod n, so it takes as input a positive integer n, and I cannot necessarily define a mod n norm residue symbol for any field. In order to define the symbol, I need to choose a primitive nth root of unity, and the symbol does depend in a mild way upon the choice of primitive nth root of unity, but probably more importantly, I need to have a primitive nth root of unity. Okay. So whenever I have a primitive nth root of unity in a field, and obviously that forces the characteristic of the field not to divide n, okay? And if the characteristic is 0, you won't have a primitive. You may not have a primitive nth root of unity. By the way, local fields have only finitely many roots of unity. That's a number 32 fact, right? But if you're in characteristic 0, then at least after you extend in the algebraic closure, you'll have a primitive nth root of unity, so you can get this after a base extension. Okay. So what is the primitive nth root of unity buying us? It is making the Galois module, or in different course, one might say finite état group scheme mu n constant. The Galois action is trivial. If it has a generator that is rational over the ground field, then obviously the Galois action is trivial. But if you think about it, the selection of a primitive nth root of unity is giving you a canonical generator of this trivial Galois module, and mapping that to 1 gives you an isomorphism. Okay, so you should think of the selection of zeta of n You should think of the existence of a primitive n-through unity makes mu-n isomorphic to z mod n as a Galois module, and the choice of zeta n gives you such an isomorphism. Okay, and conversely, every such isomorphism, you take the preimage of 1, and that gives you your primitive n-through unity. Okay, and so now we have some lovely Kummer theory here. Okay, so this is just Kummer theory, but it's very important. It's not very hard, it's not so difficult, but it's so important. So this is Kummer theory, the co-boundary map in the Galois cohomology, as we saw, as an isomorphism from the group of nth power classes into H1 with coefficients in mu-n. Okay, this is always true, I guess, to be safe, as long as the characteristic does not divide n. Okay, but again, now we know that mu-n is equal to z mod nz, so that gives us a different interpretation. H1 with trivial coefficients is a Hom. Okay, and so what is this? This is the Hom from the absolute Galois group into z mod nz. If you think about, well, of course, any Hom into a commutative group factors through the abelianization. So I could just as well write Hom from the abelian character group, abelian Galois group, but whereas a normal character would take values in Q mod z, this is taking values in z mod nz, which you can view as the n-torsion subgroup of z mod nz. So you can view this as being the group of characters of the n-torsion subgroup of the character group. These are characters whose order divides n, okay? And then you can also think of these as being, this group is dual to the abelian Galois group of exponent n. So I'm abelianizing it, and then I'm modding out by the nth powers, okay? So this gadget, take a group, abelianize it, mod out by nth powers. This is the maximal quotient of the group that is abelian of exponent dividing it. Okay, so for any group, if you take Hom from that group, I mean, these are continuous homomorphisms, in fact, which is fine. But for any group, if you take Hom into z mod nz, then you can view that as being the character group of, so in other words, the dual group of the maximal commutative quotient of dimension of exponent dividing. Okay, and again, so again, characters of a quotient sit inside characters of the group. Okay, so this is just Kummer theory, but it's super important. Okay, and then we can make it really explicit. This is, after all, just a co-boundary map. So I like it when my co-boundary maps are going from H0 to H1. That's very easy. And so what is it? So therefore, for every element of K star, I'm giving myself a character of order dividing n, right? So a character that when am I writing my characters additively? I guess I'm writing my characters additively. So a character that when I multiply it by n, I get the trivial character. And what is this? So I take this, again, this is literally just the co-boundary recipe from H0 into H1. So I take my guy, and then I choose any n through to a in the separable closure, right? And then I apply the automorphism, and I divide that by, it doesn't matter which one I choose, as long as I take the same one in both the numerator and the denominator. And then you look at this and you see that if I raise both sides to the nth power, if I raise the numerator and denominator to the nth power, I would get A. And so this thing is definitely an nth root of unity. Okay. Which I can then identify with z mod nz. Okay, so that's the Kummer isomorphism. So any element of K star is giving me, in fact, I think I'm following Harari's notation. In fact, I would like it better if I had an n in this notation somewhere, because this definitely depends upon a choice of n. Okay, so every element of K star is giving me a character. Is giving me a character on the Galois group of order dividing. Okay, and for such a guy, what is the kernel? Well, the guys are in the kernel if and only if, as you can see, if and only if this is equal to 1. So if and only if that's the case. So the field, what is the abelian extension cut out by the character, right? If every character cuts out a finite abelian extension just by taking the fixed field of the kernel. And the fixed field of the kernel is k adjoin the nth root of A, okay, which is an abelian extension because there was an nth root of unity in the ground field. Okay, so that's just Kummer theory. That's fine. And now we define our modulo n norm residue symbol, or if you like, Hilbert symbol. Okay, so this takes as input two elements of K star. Okay, and what's the definition? This is the definition. Okay, so I don't really. I mean, I guess it's reversed this way because in the previous formula, that's the way it went. As you'll see, one of the properties we'll study for this symbol is if you reverse them, you just get a minus sign. So it's not equal, but it's not the biggest deal in the world. Okay, so let's just make sure that this cup product makes sense. This is the co-boundary of the character that I just spoke about for like the 10th time. Again, I think Harari doesn't write the co-boundary symbol. He just writes chi of A either way. But because we are taking the co-boundary, it's in H2 with coefficients in Z. This again is just an ordinate. This is just an element of the multiplicative group of K. So that's 0. I guess I started writing GM for K sub star, okay, multiplicative group. And so as usual, the cup product comes out inside the inside the tensor product, and as usual. Anything tensor Z is that thing, so it comes out in second Galois homology with coefficients in the multiplicative group, which is the Brouwer group. Okay. If I get a chance, I might want to explain. So this norm residue symbol was not originally defined using Galois homology. It was originally defined as a central simple algebra with certain generators and relations. And so when n equals 2, this really is the quaternion algebra, at least it corresponds to a 4-dimensional central simple algebra over K generated by two elements I and J. The elements anti-commute with each other, and I squared is equal to A, J squared is equal to B. Okay, so this really can be thought of as defining a certain non-commutative algebra over K. This is, what does that have to do with this? Well, as I said before and haven't really talked about, the Brouwer group can also be thought of as parameterizing finite dimensional central simple algebras over K modulo a certain Brouwer equivalence relation. Okay, and so a lot of the power of it comes from the fact that you can interpret it as an algebra and you can interpret it cohomologically. Okay, so this is a very cohomological definition of the symbol. Okay, but you can't argue with it. It's a nice way of producing elements of the Brouwer group of the field. There's some really deep theorems. Let me think. So I believe it's a deep theorem of Merkuriev and Suslin from not so terribly long ago in the cosmic scheme of things, probably the 80s, that under these hypotheses, so in other words, when your field contains a primitive nth root of unity, then the subgroup generated by these symbol algebras is, yeah, I guess we're going to see in a sec. Oh, maybe I'll, okay, yeah, let me read it. So this chi, of course, is taking homomorphisms out by definition of Z mod n, which, okay, evidently these things have order n, and again, you can identify it with the entire n torsion subgroup of the character group. And so since the cup product is bilinear, it's going to take n torsion guys into n torsion guys, and so yeah, so this is not just any old element of the Brouwer group. It is an n torsion element of the Brouwer group. Yeah, okay. So the really deep theorem of Merkuriev and Suslin that I'm quoting from memory, although if you wanted to see what the theorem was and how to prove it, I just happen to have one of the few math books I have at home. Central simple algebras and Galois cohomology. I mean, I could be dramatic. I could open the book and we could find the statement of the Merkuriev-Suslin theorem. But I'm pretty sure that the statement of the Merkuriev-Suslin theorem is that if you have a primitive nth root, at least if you have a primitive nth root of unity in your ground field, then the subgroup generated by these symbol algebras is the entire n torsion subgroup of the Brouwer group. Okay, let me look it up. Let's see. Is that what the Merkuriev-Suslin theorem says? Da, 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 da. Well, it also has a K-theory interpretation. So I guess, yeah, I think it's, well, yeah, maybe I don't want to look it up right now because they're certain, it's a little complicated. Anyway, I think it, at least it implies that. Okay. Yeah. This is also related to algebraic K-theory. Okay, so right, and so these are defined for any field as long as you have a primitive nth-root of unity. Okay, and then again, if you don't have a primitive nth-root of unity, you might try to make some kind of descent argument, at least if the characteristic doesn't divide n. If the characteristic does divide n, there's a different type of symbol that you could do instead. Here we're using Kummer theory, right? And so if we wanted to do like a p power symbol and characteristic p, we should be doing something that's predicated on Ardenshire or Ardenshire-Witt theory instead of Kummer theory. Okay, so here's a very important and quite easy proposition. So the setup is exactly the same as before. So first of all, again, there is a kind of reciprocity relation between the A and the B. So for sure, if B is a norm from the finite cyclic extension obtained by joining an nth root of A. Okay, also, the splitting field of the corresponding character. So that's not a random field at all. So if B is in the splitting field of the character of A, then the norm residue symbol is equal to 0. Okay. And then just some simple algebraic relations. So for all A, B in non-zero, a symbol A paired with its negative is always 0. A paired with B is minus B paired with A. And as long as A is not equal to 1, then A paired with 1 minus A is equal to, I think this is called, maybe this is called like the Steinberg relation. Okay, which again has something to do with algebraic K-theory. And it's sad that Danny Krashen isn't here anymore because I would have told you to talk to him about it. Okay. All right. So yeah, let's the proof is really no problem. So right, so L, this K1, this is the splitting field of a character. So it's a finite abelian extension. Let's let G be the Galois group. Let me let d chi of A bar, I'm being very fastidious here, be, again, this character splits over this field, right? And so therefore, it's really inflated from the relative Galois cohomology of that field. That's what's happening. Again, think of it on the H1 side. This is a character. It's just a homomorphism. And so if the splitting field of your character is a field that the character becomes trivial when you restrict to, and so therefore every character is inflated from the Galois group of its finite abelian splitting field. Okay. I said that kind of quickly, but if you stop and think about that, that's like the least of your worries. Okay, so just because I want to line up this inflation identity, I'm going to write an overbar for that. And yeah, here's where I'm going. So a property of the cup product is that it commutes with inflation. Okay, so what the point of this is, how about I let B bar be the image of B in the Tate cohomology? Okay, so not the usual H0, which would just be in K, but the Tate cohomology, which is K modulo the norm. Okay. And so, all right, AB of n, that's a definition. That's exactly what it is. It's B tensor the coboundary of the character. And right, and so right. So this is this. So B is the inflation of B bar, and d chi of A is the inflation of d chi of A bar. Okay, so I set it up properly, and then I can commute the cup product with the inflation. And so in other words, I can really kind of compute this cup product in the relative Galois cohomology of L over K. That's what this is saying. But if I can do that, then this thing is certainly trivial because after all, what is the zeroth Tate cohomology? It's the cokernel of the norm map. What was I assuming about B again? I was assuming that B was a norm from this extension. And so therefore this B bar, my assumption is precisely that B bar is equal to 0. That is, it's in the image of the norm map. And so therefore, if this thing can be computed in this way, well, there's a 0, 0 cup anything is 0. Anyway, it's 0. Okay, so that's part A. Part B is really just some little calculation. I think for the calculation of part B, that even that it's as complicated. Oh, before I do part B, I just want to remind you that because cup products are bilinear and this norm residue symbol is defined by a cup product, then therefore the norm residue symbol is also bilinear, which is a very important property. What does that mean? Well, what does bilinear ever mean? And I've written it down. Again, we're writing, as is traditional, I guess we're writing the Brouwer group additively. At least we are here. Okay, and so now, now I'm going to prove these parts, and yeah, this proof is as you can see, it's not very complicated. This is almost the entire proof is on this page. It would be even simpler than it were if, so here you see that I'm going to be working in the field, again, the splitting field of the character. So generically, probably, this is a degree n cyclic extension, right? But it might have smaller degree if A was already a proper power for some D dividing n, okay? And so just like, honestly, you do the bookkeeping correctly, and it shouldn't really bother you that A is a proper power. It just makes the bookkeeping a little bit more difficult. Okay, so now Harari does something quite clever. So let x be any element of K such that x to the n is not equal to A. That's how the proof starts. And I read this and I got really confused for a second. I was like, x equals 0 works. Why don't we just take x equals 0? Well, he will to prove one of the parts, and then he'll take a different choice of x to prove one of the other parts. So this x is, to be named. Yes, there are such x. We're going to name some later. Okay. And then, well, you know how x to the n minus something factors. It factors via roots of unity. 1 over n. That's how it factors. Okay. So right, so here's the slight complication. Let D be the largest divisor of n such that A is a perfect Dth power. Then it's more than plausible, and you can check, this is in my field theory notes, that if A is a proper Dth power and no bigger as a divisor of n, then taking the nth root gives you a cyclic extension of degree n over D. So again, take D equals 1 at first glance, probably, to see what's happening. Okay. So then related to this, the Galois conjugates of this guy, I probably made a 1 over n here as well. So the Galois conjugates are going to be some of the other roots of unity. If A had full order n, then it would be all of them. And in general, you can check, I hope, that the Galois conjugates are the ones where the exponent is congruent to I modulo D. So again, on first reading, take D equals 1, and then the Galois conjugates are just all the roots of unity. Okay, and so then you check that x to the n minus A comes out as a product. Again, this is simpler if D is equal to 1. There's just one term here. In general, you check that it's the norm of this this expression. After all, the norm in a Galois extension is just the product of the Galois conjugates, right? Okay, so no big deal. It's this finite product of norms, and the norm is a group homomorphism. So therefore, it's the norm of something. The product is whatever this inside product is. It doesn't matter. Okay. The point being that this calculation shows us that no matter what x we take, as long as x to the n minus A is not equal to 0, x to the n minus A is going to be a norm from this cyclic extension. Okay, and now we're precisely in a position to apply what we just proved, right? So if you do the symbol A comma B, if B is a norm from the splitting field of the character of A, namely k adjoin A to the 1 over n, then the symbol is 0. So no matter what x we choose, as long as x to the n minus a is not equal to 0, we're getting a whole family of elements where the Hilbert symbol is equal to 0. So now, as I wanted to at first, if you take x equals 0, that's a good choice because minus a is not 0. That gives you the first relation that a paired with minus a is equal to 0. Now I'd like to take x equals 1, and the only problem, then I get 1 minus a, and again, you know, that's only 0 when a is equal to 1, and I'm assuming that it isn't. So if I take x equals 1 and I assume that a is not equal to 1, I get the Steinberg relation that a comma 1 minus a norm residue symbol is equal to 0. What's the last one? I just want the anti-commutativity, and that is a pretty straightforward calculation. Okay. So let's look at a comma b plus b comma a. First of all, I'm cleverly going to add a comma minus a and b comma minus b because I just proved they were both 0. And now I'm going to use the bilinearity. So this one is a, same a on the first argument. So it's a comma minus ab. Here I have the same b in the first argument. So it's b comma minus ab. Now I do bilinearity the other way. The second argument is the same. So this whole thing is ab comma minus ab. Anything comma minus that thing is 0. So that's these norm residue symbols are quite easy to work with. I actually have some papers when I do my papers where I do period index stuff in Weichet-Allais groups of abelian varieties. A lot of the actual work is done by norm residue calculations. So there is, again, the only problem is that you have to have a primitive nth root of unity in your ground field in order to do norm residue computations. And if you don't, you find yourself trying to do like descent type things. Okay. All right. The descent that we need in order to prove the theorem is like ridiculously easy. So this is going to be a favorable case. All right. So all of this was completely general, right? Class field theory, who? This was applicable to an arbitrary field with a primitive nth root of unity. Now, so for this proposition, you see I crossed out, in Harari, he says p-adic. And I realized that, in fact, you just need a primitive nth root of unity. So it'll be valid in a positive characteristic local field as long as you have a primitive nth root of unity. Okay. So what is this result saying? This is saying that the kernel, it's a pairing, right? It's a bilinear map. So you kind of want to know what the kernel on each side is. What are the guys that are annihilated by the entire, by everything on the other side, right? And so and it's skew symmetric. So the answer to what the kernel is on one side is determined what the kernel is on the other side. And so the answer is that if you're a perfect nth power, then you're going to pair to be 0 with everything. That's quite easy. That's actually true for any field. I guess the proof will probably show that. And I should have stated it that way. Anyway, and so the point of being a local field with a primitive nth root of unity is that now you get a non-degeneracy in the pairing. So the reverse implication is true and is much more exciting. The only elements that pair trivially with every element of the field under this mod n norm residue symbol are the ones that are nth powers. Okay, so what does this mean? This means that, first of all, since every nth power pairs to be 0 with everything, then the pairing really just, if you like, the pairing really is a pairing on nth power classes. Okay, and again, this is true for any field which has a primitive nth root of unity. In general, it would land in the Brouwer group, which is quite complicated, or the n torsion of the Brouwer group, right? But for the local field, this turns out to be Q mod Z, which is kind of like a duality. And so yeah, so what we're saying here is that for a local field containing a primitive nth root of unity, this mod n norm residue symbol is a perfect pairing. Okay, so in other words, it identifies. I guess I'm saying it's non-degenerate, but since the groups are finite, if you think about it, Yeah, so I'm saying that this pairing identifies each of these finite groups with the dual of the other one. Okay, so whatever, it's a, probably you guys have seen what a perfect pairing is. It's a perfect pairing. Okay, any questions before I prove it? No, no questions. All right, not so bad. Yeah, so again, the first implication is true for any field where these things are defined. So I probably should have said it that way, following Harari. So I take my A star, so K1, there's many ways to see that 1 implies 2. So here's one. So again, as we said, this extension, if you have an nth root of unity and you take the nth root of something, you're certainly getting a cyclic extension of degree dividing n. Let's, just as before, we called the degree d, let me call it d. What's the point? Well, then if you're an nth power and d divides n, then you're certainly a dth power, okay? And since this is an extension of degree d, then certainly every, in any field extension of degree d, the dth powers are norms from the extension. They're norms of downstairs elements, right? If you take a norm of a downstairs element, you just raise it to the degree of the field extension. Okay, so evidently everything that is an nth power is a norm from this extension. And we just said that if you pair anything, if you pair any b with an element that is, if b is a norm from k join a 1 over n, then ab is 0. Okay. So that works. And as you see, I certainly have not used this holds for any k. We certainly have not used that the field is local for that. Okay. For the other one, we are. So now suppose that AB pairs, suppose that B is such that it pairs trivially with every, that was a typo. Sorry, yikes, that was maybe a bad typo. I didn't mean to have an nth power there. Right, so suppose that B pairs trivially with everything. Well, it's skew symmetric, so if you did it the other way, it would pair to be 0. And so in particular, A cup d chi B is equal to 0. And so what's the point? Again, this is this identity that I was talking about before. It's our friend. The invariant map of this cup product kind of simplifies as just the character evaluated at the reciprocity map of the element, okay? But if A cup d chi B is 0, well, if it's 0, you apply something, you get 0. So this whole thing is going to be equal to 0. But now this holds for every element in K star. And you think about this, since the image of K star inside of the abelian Galois group is dense, as we well know, that was actually kind of the easy part. And this chi is actually a continuous character, right? Everything by definition, we mean them to be continuous characters. And so what does that prove? That proves that this character vanishes on a dense subspace of a topological space. Everything's Hausdorff, therefore the character is 0, 1, I don't know. It's the trivial character. So again, what does it mean for chi b to be the trivial character? The splitting field of chi b was, well, the splitting field of chi a was k adjoin the nth root of a. So the splitting field of chi b is k adjoin the nth root of b. And so yes, we've assuming that b pairs trivially with every a, we got that the corresponding character is trivial, therefore its splitting field is just equal to k, and that does tell us that b is a perfect nth power. Okay, so we're really reaping some benefits here. Okay, so the norm residue symbol is a perfect pairing on the nth power classes of a local field containing a primitive nth root of unity. That's an important result. Okay, here we go. Now we are ready to prove, or at least we'll see if we get through it. Probably we will. So the existence theorem now for p-adic fields. Okay. So okay, I'm just going to state it carefully, although it's pretty clear. So okay, I have a p-adic field with algebraic closure K bar. if I have a finite index subgroup, again, we've explained that in characteristic 0 and not in characteristic P, every finite index subgroup of the group of units of the field is open. Okay, so we don't have to say that it's open. Then there exists, and we've already proven that it's unique, every finite index subgroup is the norm subgroup of some finite abelian extension. Okay, so this is what we therefore they intersect trivially, because the intersection of all the finite index subgroups of K star is certainly trivial. Okay. All right. Yeah. Okay. So let's prove it. So first of all, this is a trick that we've used several times already. If I have a commutative group G and I have a subgroup of finite index, let's say H is a subgroup of index N, then H must contain the subgroup of nth powers of elements in G. Okay. This is useful like all over the place, right? Okay. Why is that? It's easy because if you look at the composite map from Gn injecting into G via the quotient map, then once you live in the quotient, you're looking at therefore you're looking at elements in this group of order n that are nth powers. Okay, and so like by a special case of Lagrange's theorem, you know, if I have a finite commutative group of order n and I raise anything to the nth power, I must get 0. Okay, so that composite map is trivial, and therefore Gn is contained in the kernel, which is H. Okay, so what does this mean? It means that any index n subgroup has to contain the nth powers. And now is where we're very lucky that K is p-adic. We know that the nth powers itself is a finite index open subgroup of K star. Okay. This is not something in number theory too. Not only do we prove that the nth powers have a finite index in K star for a p-adic field, we actually compute what the index is. Okay, which takes some work, but for sure it has finite index. And this is where the proof breaks down. If I were in a, by the way, if I were in a positive characteristic local field, there's this, an n here is going to be introduced, and if we just assume that n was prime to p, then then the proof would go through in the positive characteristic cases as well, but it wouldn't go through at p because the pth powers have infinite index in a Laurent series field. Okay, right. And so what's the point? We know a lot. We know that any subgroup that contains a norm subgroup is also a norm subgroup. We proved that apparently on page 5 of the last lecture. Yeah. So if you have a finite abelian extension, we got this Galois correspondence between open subgroups of K star containing the norm of the extension and abelian subextensions. And so in particular, as I said, every subgroup bigger than n of L star is also the norm of the corresponding abelian subextension. Okay. So it's enough to show that sufficiently small finite index subgroups are norm subgroups. And if we're in characteristic 0, then that's the point. The nth powers are already cofinal in all of the finite index subgroups ordered under reverse inclusion. Right? I mean, how do I, again, I said something, how did I really know that the intersection of all the norm subgroups was trivial if I knew that how do I know that the intersection of all the finite index subgroups of the multiplicative group was trivial? Well, for instance, the intersection of all the nth power guys, these are elements of a p-adic field that are nth powers for all n. And it's easy to prove that if you're an nth power for all n, then you have to be 1. Okay. All right. So, okay. So that all I need to show is that K star to the n is a norm subgroup. So I need to explain which finite abelian extension, if I take norms from it, then I get precisely the nth powers. Okay. And it turns out that this is easy to do as long as I can assume that K contains the primitive nth roots of unity. So the next thing I'll do is reduce to that case. Okay. So I want to reduce to the case where K is a primitive nth root of unity. Watch how easy it is. Again, this type of descent argument is often more of a pain than this. So since the characteristic is 0, of course, there's an nth root of unity in the algebraic closure. If I take F to be K adjoin a primitive nth root of unity, it's an extension of degree dividing phi of n, so it's still a p-adic field. Okay? And so suppose that I can solve the problem over here. So suppose that after I join the primitive nth root of unity, then I know that the nth powers are the norm of a finite extension of F. Okay, watch how easy this is. Well, the norm is a homomorphism. So the norm of F over K takes elements of F star into elements of K star. So like any group homomorphism, it takes nth powers to nth powers. So certainly K star to the n contains the norms of nth powers over there. What did I assume? I assumed that the nth powers in my extension F were precisely the norms from some finite extension E. Okay, so I do that, and then I look at this and I say, I have the norm from F down to K of the norm from E down to F of E star. Oh, the norm is transitive. So that is the norm of some extension E down to K. And if you think about it, you're worried that, so what do I have here? I have my K, I have my F, which is K zeta n, and then I have my E. And I could have chosen, I did choose my E to be abelian. And then you say, hey, wait a minute, that's not the way Galois extensions work. Just because this thing is abelian and this thing is abelian does not mean that the tower is abelian, right? Right, but we don't have to worry about that because remember, one of the things that that followed from what we did was pretty easy, that we had a result about the norm of any finite extension of local fields. The set of norms from an extension is precisely the set of norms from the maximal abelian sub-extension of that extension, right? Because each one was isomorphic to the Galois group of the abelianization. Okay, so we get the norm from E star, which if you didn't like that it was not an abelian extension, then you just take E prime to be the maximal abelian sub-extension of E over K. And what did that show? That shows that K star to the n, if we can solve our problem over F after adjoining a primitive nth root of unity, then we've shown that K star to the n, which we want to be a norm subgroup, contains a norm subgroup. And once again, we previously proved that if you contain a norm subgroup, then you are a norm subgroup. Okay. So we have successfully reduced to the case where our local field contains a primitive nth root of unity. Okay. And again, this if I'm just trying to prove that K star to the n is a norm subgroup, which is sufficient in the p-adic case, if n were prime to p, this argument would still work to prove that K star to the n is a norm subgroup in the Laurent series case. It just doesn't prove the whole thing. Okay, so now Kummer theory and the norm residue symbols finishes out for us. Okay, so this is the Kummer theory that we've seen before. K star by K star to the n is the sort of mod n character group. Okay, so that's chi of the abelianization modulo its nth powers. We know that K star mod K star to the n is finite. Again, we're in a p-adic field, so thank goodness. And so therefore, these are isomorphisms. So therefore the character group is finite. Therefore the actual mod n Galois group is finite. So what is this? This is some finite quotient of the Galois group of K. And so therefore it is a quotient by a closed subgroup. So therefore it is the automorphism group of a finite abelian extension. Which finite abelian extension, if you just think about it in terms of the Kummer theory, then for any field, this guy is going to be the automorphism group of the maximal abelian extension of exponent dividing n. Okay, you just take the composite. If I take the compositum of any number of abelian extensions of exponent dividing n, I get another abelian extension of exponent dividing n. I do that. Okay. By Kummer theory, since a primitive nth root of unity is in the ground field, more explicitly, how do I get L sub n? I just adjoin nth roots of everything. Okay, and that's why I do it. And I know, how do I know that I'm getting a finite extension? Because I know that the set of nth power classes is finite. Okay. So this Ln is pretty concrete, is what I'm saying. It is the maximal abelian extension of k of exponent dividing n, which is finite precisely because the group of nth power classes is finite. And okay, its order is whatever this is, which I know what it is from number theory 2. And now I'm trying to find a finite abelian extension whose norms are precisely the nth powers. Guess what? It's going to be this. Okay, so Ln, my maximal abelian extension of exponent dividing n. By the way, it is actually going to turn out to be equal to n in this case, and that is my group. So the norm of Ln is going to be the nth powers. Let's prove it. Yep, that's my claim. So let's see. On the one hand, this is our reciprocity map. We know that case reciprocity map induces this type of isomorphism. Okay, that was true for any finite abelian extension, right? We proved that long ago. And again, I just told you, I guess I forgot that I put an n on it. So L sub n, that is the automorphism group. The automorphism group is the maximal abelian quotient of exponent dividing n. And so let me just write W sub n to be this reciprocity map followed by this quotient map. And okay, it's completely, I took an isomorphism and then I followed by this this surjective map. So that's not the right way to say it. this map here is this thing that I'm calling, yeah, basically I'm taking Wn really is just taking W and pulling it back to K. Yeah. Okay. Because this thing is the automorphism group of L over K. Anyway, so the kernel of this map is visibly the norms from this extension. So that's one way to look at it. So on the other hand, I want to look at this map in a different way and show that the kernel is the nth powers. Okay. Well, the target of this map is a commutative group of an n-torsion commutative group. So if you take something that's an nth power and you map it into an n-torsion group, obviously that's mapping trivially. So the easy part is to see a lot of indices that this is to see that the nth powers are in the kernel. Okay, so the matter of it is to show that everything that's in the kernel of this reciprocity map is actually an nth power. Okay, because then we'll know that on the other hand, the kernel of this map is precisely the nth powers, whereas just by the class field theory setup, the kernel had to be the norms. Okay, and this is just going to be exactly what we've already developed. So, okay, so let me take an element in the kernel, take an arbitrary element of K. By definition, the norm residue symbol is that cup product. Okay. So let's see, what do we know? We know that when I apply this thing to B, then I get something which is in the nth power of the abelianization. Yeah, that's just what it means to be in the kernel of this map. Right? Okay. So that is certainly true. Wait, let me just think for a second. Yeah, sure, of course. If you get killed over here, then what does it mean to go to 0 in this group? It means that you're in the thing you modded out by. So sure. So omega of B is in the nth powers of the abelianization. Okay. Now we have this, but again, this character was n-torsion as we discussed. It was constructed that way. And so, okay, well then, if I take a character that has order that is n-torsion and I evaluate it at an nth power, then I'm going to get 0. Okay. This omega b is n times something else, and so I pull out the n, and n times chi of a is equal to 0. But on the other hand, I use this, this formula that I mentioned once already in this lecture. Character evaluated at reciprocity map of B is also B cup D of the character, take the invariant map. So therefore, I just learned that the invariant map of this thing is equal to 0. The invariant map was an isomorphism. So whatever was inside was 0, but whatever was inside is on the nose the norm residue symbol. Okay. And so what did we just show? We just showed that whatever A you picked, you paired A with B, and the norm residue symbol was 0. Well, we just proved that that means that B is an nth power because it pairs, because it's in the kernel of the parent. And we're done, because we clearly, on the one hand, the kernel of this map is certainly the norm subgroup of this this extension Ln. On the other hand, we showed that the kernel is precisely the nth powers. Again, the tricky part was showing that the kernel isn't any bigger than the subgroup of the nth powers. That was the non-degeneracy of the norm residue symbol. Okay, so yeah, we are done. And then the corollary is as follows, as promised. So now we know that that this reciprocity map induces an isomorphism on the profinite completion. Again, the only thing that we needed to know was what the kernel was, and we just proved that the kernel was 0. Okay, and so therefore, yeah, so therefore this, my friends, is local class field theory for a p-adic field. This canonical reciprocity map upon passage to the profinite completion induces an isomorphism from the profinite completion of the unit group of the field to the abelian Galois group. So in particular, it induces a bijection between finite index subgroups of the multiplicative group of the field and finite abelian extensions of the field. And then again, as we saw before, the interesting part of this, again, there's a piece of this, which is the profinite completion of Z, right? And we didn't need class field theory to help us figure that part out. That part was the maximal unramified extension. Of course, the maximal unramified extension of a local field with finite residue field is isomorphic to Z hat. The complementary piece is the unit group, right? So K star is isomorphic to Z hat across the unit group of the valuation ring. And again, the only thing left that we had to prove was the fact that this map was injective. And so this map is the restriction of this injective map. And we already saw that the reciprocity map carried the unit group surjectively onto the abelianized inertia group. And so most of the content of local class field theory is telling us the structure of this, the totally ramified piece of the abelian Galois group. Okay, it is canonically isomorphic to the unit group of the field. Okay. In particular, that means it's isomorphic to ZP to the degree of the field over QP directs on a finite group. Okay. Okay, so that's basically the end. I think I said this before. This method would definitely give you something if you applied it to a Laurent series field, and instead you just have to stay away from P, right? We say, if in everything that I did, I say, let me only look at finite index subgroups of K star whose index is prime to P, then they're all open and everything else works, and it's fine. And so if you wanted to formalize that, I think that this method would show if on both sides, we just have profinite commutative groups, so they're the product of their CELO P subgroups. And so if on both sides you just mod it out by the CELO P subgroup, then you would get an isomorphism. So you get an isomorphism kind of on the prime to P part of the profinite completion of K star with the prime to P part of the abelian Galois group. So that's definitely something. On the other hand, it's supposed to be true at P as well. And so the next thing that I'll do is I'm going to do the Lubin-Tate stuff. And the Lubin-Tate stuff is a kind of local field generalization of complex multiplication, like I said, so that sounds nice. And the Lubin Tate stuff will give the full result in the positive characteristic case as well. Okay, any questions? Well, that's local class field theory for p-adic fields, so yay! You should probably think it over for a bit, you know? Okay, well, see you soon.